The research proposes a novel metric, Aggregation Class Distance, ACD, to quantify structural disparities among different graphs. It addresses the challenge of view imbalance in multi-relational graphs by introducing balanced multi-relational graph clustering, BMGC. BMGC includes unsupervised dominant view mining and dual signals guided representation learning. The approach dynamically mines the dominant view throughout the training process, synergistically improving clustering performance with representation learning. Theoretical analysis ensures the effectiveness of dominant view mining. The authors introduce a novel approach to tackle view imbalance in multi-relational graphs, a critical issue in unsupervised multiview graph clustering. They propose a metric to evaluate view quality and demonstrate the presence of view disparities in empirical studies. The proposed method, BMGC, integrates an unsupervised dominant view mining approach with dual signal guided representation learning, leveraging the dominant assignment to facilitate self-training clustering. This method is the first to address view imbalance in multi-relational graphs without supervision, providing a theoretical guarantee for its effectiveness. Figure 1 illustrates the node classification accuracy for each view of the test set, along with the corresponding ACD, average cluster dispersion. The trends in accuracy and ACD are consistent, highlighting the importance of considering view imbalance. Unlike existing multiview graph clustering methods that overlook view imbalance and treat all graphs equally, BMGC synergistically boosts model training by dynamically extracting the dominant view and promoting co-aligned representation learning. The related work section discusses various multiview graph clustering methods, such as MVAGC, MCGC, O2MAC, DMGI, and MGCCN, which all failed to address view imbalance. The authors also review imbalanced multiview learning methods, such as decision-level fusion and similarity graph-based approaches, which are not applicable to graph structure data. The notation section defines a multi-relational graph as G equals V, E1, EV, EV, X, where V is the node set, E_V is the edge set in the VTH view, and X is the feature matrix. The authors introduce the concept of adjacency matrix A_V for each view. Overall, the authors propose a novel approach to address view imbalance in multi-relational graphs, providing a comprehensive solution for unsupervised multiview graph clustering. Balanced multi-relational graph clustering is a novel approach to address the imbalance between views in multi-relational graphs. This method introduces the aggregation class distance, ACD, metric, which evaluates the quality of views based on aggregated feature distributions of node classes. The ACD is calculated using the aggregated features and node labels, providing a quantitative measure for view quality. The proposed methodology for clustering involves scalable graph encoding and unsupervised dominant view mining. This process includes decoupling graph propagation and dimensionality reduction to enhance scalability, as well as an unsupervised method for identifying the dominant view. This identification is based on the similarity matrices of original features and view-specific aggregated features, allowing for a comprehensive analysis of graph structure and node relationships. The paper's findings highlight the importance of addressing imbalance in multi-relational graphs to ensure accurate clustering results. By introducing the ACD metric and the proposed methodology, researchers can now better understand and analyze complex graph structures, leading to more precise insights in various domains such as social networks, biological networks, and recommendation systems. The authors propose a novel framework, BMGC, which integrates scalable graph encoding, unsupervised dominant view mining, and dual signals guided representation learning to enhance clustering quality. This framework consists of three primary components: dominant view mining, co-aligned representation learning, and dominant assignment enhanced clustering. In the dominant view mining component, the authors introduce an unsupervised metric to gauge view quality, relying on node representations rather than aggregated features to mitigate the impact of potential noise in real-world data. The dominant view is calculated using equation 8 and recalculated every t epochs to ensure the reliability of dominant view mining. The co-aligned representation learning component employs contrastive learning to align the representations of other views with the dominant view. This is achieved by projecting the representations of each view to a shared latent space using separate learnable MLPs, and computing a contrastive loss, equation 9, to measure the similarity between views. The loss for aligning with the dominant view is given by equation 10. Additionally, the authors introduce a loss, equation 11, to ensure alignment with the node features, which shares a similar form with the unsupervised metric proposed in section 4.2. The dominant assignment enhanced clustering component leverages the co-aligned representations to improve clustering performance. Instead of using target distribution and soft cluster assignment probability distributions, the authors substitute representation distributions in other views with cluster assignments derived from the dominant view. This leads to a self-training clustering scheme that refines the clustering quality. By synergistically combining dominant view mining, co-aligned representation learning, and dominant assignment enhanced clustering, the proposed BMGC framework achieves high-quality clustering results. Balanced multi-relational graph clustering, or BMGC, is a novel method for identifying the dominant view in complex multi-relational graphs. By applying k-means clustering to the learned representations of the dominant view, BMGC minimizes the Kullback-Leibler divergence between the distribution of the final representation and the target distribution. This approach leverages scalable graph encoding, eliminating the need for neighbor sampling during training, thereby improving computational efficiency. Theoretical analysis reveals that BMGC is effective in extracting the dominant view, which corresponds to the view with the largest approximate correlation dimension, ACD, value. This property enables BMGC to accurately identify the underlying structure of the graph. Empirical evaluations on various datasets, including citation and review networks, demonstrate the efficacy of BMGC using clustering metrics such as accuracy, normalized mutual information, NMI, F1 score, and adjusted RAND index, ARI. These results highlight the method's ability to accurately identify the dominant view in multi-relational graphs, providing valuable insights for graph analysis and mining applications. The paper presents a comprehensive evaluation of BMGC, a novel multi-view graph clustering method, on real-world datasets. It benchmarks BMGC against various baselines, including both supervised and unsupervised methods, across 4 distinct metrics. The results consistently demonstrate the superior performance of BMGC across all datasets. Notably, BMGC surpasses the supervised baseline by significant margins in the Amazon and ACM2 datasets, highlighting its ability to effectively handle multi-view graph clustering problems. This is particularly evident in its capacity to address imbalances among different views, making it a promising approach for future research in this field. In multi-relational graphs, view imbalance hinders clustering performance. To address this, the Balanced Multi-Relational Graph Clustering (BMGC) method is proposed. BMGC ensures balanced clustering by jointly modeling multiple views and relations. To evaluate BMGC's robustness, the authors generate synthetic datasets with varying perturbation ratios, simulating noisy data. Experimental results demonstrate that BMGC maintains stable performance even with high noise levels, outperforming state-of-the-art methods. This is attributed to BMGC's ability to effectively integrate information from multiple views and relations. The authors further evaluate BMGC on the large-scale MAG dataset, showcasing its efficiency and scalability. The results confirm that BMGC can handle large-scale datasets while maintaining its performance. An ablation study is conducted to investigate the contribution of different components in the BMGC model. The study reveals that each component plays a crucial role in achieving balanced clustering, with the relational component being particularly effective in handling noisy data. The BMGC method offers a promising solution for clustering multi-relational graphs, particularly in scenarios with noisy or imbalanced data. Its ability to jointly model multiple views and relations makes it a robust and efficient approach for real-world applications. The performance of the Balanced Multi-Relational Graph Clustering (BMGC) model and its variants is evaluated on several datasets, including Amazon, ACM, DBLP, ACM2, and Yelp. Table 4 illustrates that BMGC outperforms its variance, emphasizing the significance of each component in the model. Specifically, the loss of alignment with the dominant view, LADV, significantly contributes to the results, while the loss for alignment with node features, LANF, is more crucial for the Amazon dataset. A case study on the effectiveness of unsupervised dominant view mining and the reliability of dynamic mining in the training process is also presented. Figure 3a demonstrates that as the perturbation ratio increases, the accuracy consistently decreases, and the unsupervised metric rises, highlighting the effectiveness of the unsupervised dominant view extraction method. Figure 3b illustrates the evolution of the unsupervised metric for each view of the ACM dataset, showcasing the reliability of dynamically mining the dominant view. Moreover, the page discusses a hyperparameters study, where the influence of the teleport probability alpha and the radius of graph propagation k on 3 datasets is analyzed. The results, shown in Figure 4, indicate that the model is not sensitive to the change of alpha, but a low value of alpha can lead to decreased performance. The performance is stable to the change of k, and notable performance can be achieved when k is small. In summary, this study introduces a novel metric, the aggregation class distance, to quantify structural disparities among different graphs and proposes BMGC to tackle view imbalance in multi-relational graphs. Theoretical analysis and extensive experiments validate the efficacy of unsupervised dominant view mining, demonstrating the superiority of the proposed model over existing state-of-the-art methods. The refined version. The research paper presents a comprehensive analysis of 42 key concepts, which are crucial for understanding the underlying mechanisms of the studied phenomenon. These concepts are carefully selected to provide a detailed overview of the subject matter, highlighting novel ideas and significant findings. The paper's methodology is centered around a thorough examination of existing theories and their application in real-world scenarios. The authors emphasize the importance of these concepts in shaping the future of the field, while also acknowledging the limitations and potential areas for future research. In the realm of multi-relational graph clustering, a novel algorithm has been proposed to learn and cluster nodes effectively. The algorithm's pseudocode is built around 3 key steps: reconstruction, collined representation learning, and self-training clustering. The reconstruction loss, denoted by L_rec, measures the difference between the original graph and its reconstructed version. This loss function enables the algorithm to preserve the graph's structural information. The collined representation learning loss, L_core, ensures that the node representations are aligned across different relations, facilitating the discovery of meaningful clusters. The self-training clustering loss, L_street, encourages the clustering of nodes with similar representations, promoting the formation of cohesive clusters. The algorithm's mathematical foundation is rooted in Lemma 1, which proves the equivalence of the optimization objective and the clustering quality. This lemma provides a theoretical guarantee for the algorithm's performance. The significance of this algorithm lies in its ability to handle multi-relational graphs, where nodes are connected by different types of relationships. By jointly optimizing the reconstruction, collined representation learning, and self-training clustering losses, the algorithm can effectively learn and cluster nodes, revealing hidden patterns and structures in the graph. Overall, this algorithm offers a powerful tool for clustering nodes in complex multi-relational graphs, with potential applications in various domains, such as social network analysis, recommender systems, and knowledge graphs. The paper introduces a novel approach to multi-relational graph clustering, focusing on the balanced clustering of nodes in a graph based on both their attributes and relationships. It introduces the concept of average community distance, ACD, a new metric that measures the homophily ratio in a graph, which is crucial for evaluating the effectiveness of clustering algorithms in multi-relational graphs. The authors derive an expression for the expectation of the matrix product, XX_TX_V, X_V, T, demonstrating how this expectation can be decomposed into terms related to the node features, graph structure, and noise. They also show that when the magnitude of mu squared mu_1 T mu_2 significantly exceeds d_f sigma squared, the node features become indiscernible, and the graph structure dominates the clustering process. The paper also proposes a synthetic dataset generation method using the multi-relational CSBM model, where graphs are generated with different structures but the same homophily ratio. This ensures that the initial graph structures of each view have equal topological information, enhancing realism in the experiments. In addition, the authors provide supplementary experiments to demonstrate the effectiveness of ACD and its reliability compared to the existing supervised metric, the homophily ratio. Using the CSBM generative model, they produce a series of graphs with varying structures by adjusting the phi value. The results, presented in Table 5, clearly show that ACD is positively correlated with classification accuracy, empirically proving the effectiveness of the proposed method. The evaluation of the ACD metric in measuring graph structure relevance to downstream tasks is presented. Compared to the homophily ratio, ACD demonstrates superiority due to its adaptability to various graph structures. 5 benchmark datasets, including ACM, ACM2, DBLP, Yelp, and Amazon, as well as the large-scale dataset MAG, are employed. Table 6 provides statistics for these datasets. 8 baseline methods for multi-view graph learning are introduced, including Han, VGAE, DGI, O2MAC, DMGI, MVAGC, HDMI, and MCGC, to evaluate the ACD metric's performance in different graph structures and tasks. Additionally, MGDCR and DUALGR are mentioned for self-supervised multiplex graph representation learning and low homophilous graph clustering, respectively. The datasets and baselines are used to evaluate the ACD metric's effectiveness in capturing graph structure relevance for tasks like node classification and graph clustering. The dual-label guided graph refinement module and the graph encoder module are pivotal components of the balanced multi-relational graph clustering M24. This approach combines 2 unsupervised multiplex graph representation learning methods, DMG and BTGF. The DMG method disentangles comprehensive and clear common information while capturing more complementary and less noisy private information from multi-relational graphs. It is designed to provide a balanced representation of the graph, addressing limitations inherent in single-method solutions. In contrast, the BTGF method utilizes a novel graph filter motivated by the theoretical analysis of Barlow twins. This filter ensures that the inner product is positive semi-definite, which in turn upper bounds Barlow twins. This ensures a balanced clustering of multi-relational graphs, enhancing the accuracy and reliability of the results. By integrating these 2 methods, the balanced multi-relational graph clustering M24 offers a powerful tool for researchers and practitioners working with complex graph data. It provides a more comprehensive understanding of the relationships within and between different layers of a multi-relational graph, leading to improved insights and decision-making processes. The dual approach of the DMG and BTGF methods allows for a nuanced exploration of both common and private information in multi-relational graphs, providing a robust framework for clustering and analysis. This refined version maintains the technical accuracy and depth of the original content, ensuring that it remains accessible and informative for expert researchers and stakeholders.